Let's talk about time. You know, that thing that's always ticking away in the background of our lives. We plan our days by it, we measure our lives with it, and we just assume that it's the same for everyone everywhere. But what if it's not? What if your clock and my clock and a clock on a satellite are all experiencing time just a little bit differently? Well, thanks to Einstein, we know they are. And today we're going to dive into why your clock isn't universal.
So let's just ask it straight up. Is time the same for everyone? For pretty much all of human history, the answer was an obvious of course it is. But it turns out the universe is a lot stranger than we thought. Modern physics tells us that time is actually personal, it's flexible, and it depends entirely on where you are and how fast you're moving.
You see, for centuries, we had this idea from Isaac Newton that time was like a giant cosmic clock, a universal metronome, ticking away at the exact same pace for everybody, no matter what. It was absolute. But then along came Albert Einstein, and he just completely turned that idea on its head. He said, no, time is relative. It can be stretched, it can be squeezed. It all depends on your speed and the pull of gravity.
So that brings us to our first section. Time isn't what you think. And this wasn't just some small adjustment to the old theory. This was a full-blown revolution that gave us a completely new way to understand the entire universe. Which leads us right here to your phone's Einstein connection. Now, I know this all might sound like super abstract, theoretical stuff that only physicists and labs care about, but the truth is, this mind-bending science is at work every single day, and it's probably in your pocket right now. Yeah, you heard that right. Every single time you pull up a map to find your way or check to see how far away your ride is, you are using Einstein's theories. The Global Positioning System, or GPS, is built entirely on these insights about time. To put it bluntly, if we ignored relativity, your GPS would be completely, utterly useless. Okay, so here's how it works. There are two big effects at play. First, you've got special relativity. The GPS satellites are zooming around the Earth at about 14,000 kilometers an hour. That incredible speed means their clocks actually tick slower than ours down here on the ground. The difference? About 7 microseconds every single day. But wait, that's only half the story. There's another, even bigger effect from general relativity. Those satellites are way up there, about 20,000 kilometers high, where Earth's gravity is much weaker. And because of that weaker gravity, their clocks actually tick faster than ours, by a whopping 45 microseconds per day. So you've got one effect slowing time down and another one speeding it up. When you put them together, what do you get? Well, the speeding up part wins. Every single day, the clocks on those GPS satellites get ahead of the clocks on Earth by 38 microseconds. Now that sounds like an impossibly small amount of time, but it makes all the difference. And this chart really drives the point home. If we didn't correct for that 38 microsecond drift, the error in your location would grow by about 11 kilometers every single day. After just one day, your phone would think your house is in the next town over. It would be useless in minutes. That's why engineers have to build Einstein's equations right into the system, pre-correcting the clocks to keep them in sync. So let's dig into that a little more. Section 3, Speed versus Gravity. The GPS example is perfect because it shows us the two main ways time gets warped. Physicists call this phenomenon time dilation, and it really does have these two different phases. First up, you've got kinetic time dilation. This comes from special relativity. The basic idea is that there's a cosmic speed limit, the speed of light, and nothing can break it. For that rule to hold true for everyone, something has to be flexible, and that something is time. So the faster you zip through space, the slower you have to travel through time. It's like a trade-off. Then you have the other side of the coin, gravitational time dilation. This one comes from general relativity. Here the idea is that massive objects like planets and stars don't just sit in space. They actually warp the very fabric of space-time around them. Think of a bowling ball on a trampoline. The stronger that gravitational pull, the deeper the curve and the slower time itself flows. It's wild, but a clock on a mountaintop really does tick faster than one at sea level. Now, here's a really important, kind of tricky distinction. The time dilation from speed is reciprocal. It's all about your point of view. If you flew past me in a spaceship, I would see your clock ticking slow. But from your perspective, you'd see my clock ticking slow. We'd both be right. But gravitational time dilation is absolute. Everybody in the universe, no matter where they are, would agree that the clock closer to the planet is the one that's running slower. It's not a matter of perspective, it's a measurable fact. So, okay, I know what you might be thinking. This all sounds like science fiction.
how do we actually know any of this is real? Well, that's what our fourth section is all about: racing clocks and cosmic rays. Scientists have come up with some brilliant experiments that prove, without a shadow of a doubt, that time really does change.
One of the coolest proofs actually comes from nature itself. There are these tiny particles called muons that are created when cosmic rays hit our upper atmosphere. Now, these muons have an incredibly short lifespan, so short, in fact, that they should all decay and disappear long before they ever reach the ground. But here's the thing. We detect them on the ground all the time. Why? Because they're traveling at nearly the speed of light, their internal clocks slow way, way down, giving them enough time to finish the journey. It's a perfect, natural experiment.
But the real smoking gun came in 1971 with something called the Hafele-Keating experiment. It was genius in its simplicity. They took super precise atomic clocks and put them on commercial passenger jets. They flew them around the world, once heading east and once heading west. And just look at the data. The time shifts they measured were almost exactly what Einstein's theories predicted they would be. The clock flying eastward, moving with the Earth's rotation, lost a tiny bit of time. The one flying westward against the rotation gained time. It was definitive proof.
All right, we've established this is real, it's measurable, and it's happening all around us. So for our next section, time at the extremes, let's take this idea and just crank it up to 11. What happens when you go to the most extreme places in the universe? This is where it gets really mind-bending.
If you've ever seen the movie Interstellar, you've seen the most famous example of this. Remember Miller's planet, the one orbiting the giant black hole? 1 hour down there was equal to 7 years for the guy waiting in the spaceship. That's a time dilation factor of over 61,000. And here's the crazy part. The physicist who advised on the movie confirmed that, mathematically, it's totally plausible. That's the power of a black hole's gravity.
But you don't need a black hole to find these massive effects. It's happening right here, right under our feet. Earth's core is buried under thousands of kilometers of rock, meaning it's in a much stronger gravitational field than we are on the surface. Because of that, time in the core has been ticking just a little bit slower for the last 4.5 billion years. The result? Earth's core is literally 2.5 years younger than its crust. And this just shows you how much the sheer mass of an object matters. If 2.5 years on Earth sounds like a lot, just take a look at our sun. With its immense gravity, the time difference is staggering. The core of the sun is about 40,000 years younger than its surface. Incredible. So where does all of this leave us? In our final section, the universe's local time, we have to pull it all together and ask what this really means. The inescapable conclusion is that we have to completely throw out the idea of a single universal time. Time is a local phenomenon. So let's recap the big takeaways. First, this isn't just theory. Our modern life literally depends on it. Second, the age of something isn't a fixed universal number. It's just a local measurement. Third, this affects everything. It's not just clocks, it's chemical reactions, it's biological aging, the whole shebang. And finally, this is not some weird exotic effect that only happens near black holes. It's a constant, fundamental feature of our universe, happening everywhere all the time. There's a quote from the source material that puts it perfectly, even if it is a bit technical. What it's really saying is that time isn't a fixed ruler that we use to measure events. It's more like a dynamic, flexible thread woven into the fabric of spacetime, and it's constantly being tugged and stretched by every bit of energy and matter in the universe. And that leads us to one last, big, mind-blowing question to leave you with. If time is truly local, if my now is different from your now, and both are different from the now on a distant star, does a single, universal now that we can all point to and agree on even exist? It's a pretty deep thought. Thanks for joining me on this one.